In this video, I'm going to explain why it is true that the sine of some angle theta is approximately theta. So if you want to calculate sine of 0.1, you can do it in your head. It's approximately 0.1. A very quick, easy formula. And this works if theta is in radians. So if you do it in degrees, it won't work. Radians. And theta has to be small. Theta is small. And by small, we mean close to 0. And we'll see in the demonstration why it is true that it has to be in radians and why it is true that theta has to be small. Basically, the simple version of this is a sort of picture proof. We're going to start with a circle. So here is a circle. And we're going to make some angles in the circle, and we're going to make some triangles in the circle. And by looking carefully at these angles and triangles, it's going to explain to us why it is true that the sine of theta is approximately theta. So very simply, here I have drawn some angle theta in purple. It's 0.588 radians in this example. And I have drawn a red triangle inside the arc made by theta. So theta is a purple arc. It's a little like pie piece of the circle. And this red triangle that lives inside that pie piece is a little bit smaller than the whole purple pie piece. And by looking at this triangle, we're going to see why it is true that the sine of theta is approximately theta. And what we're going to do is we're going to compare these two lengths. We're going to compare the length of the arc length of this piece, this purple arc length, to the height of the triangle. And I wrote this height as h small. It's a smaller triangle, so that's the height of the small triangle is h small. And because we're working in radians, and because it's the unit circle, a circle of radius 1, that means that this arc length is exactly theta. So the arc length on a unit circle is exactly the number of radians of that arc, which is exactly theta. So this height is h small, this distance is theta, and by looking at the picture, we can see that h small is less than theta. And this works no matter what angle you pick. So no matter what angle you pick, it's always going to be true. On the other hand, h small turns out to be exactly the sine of theta, and we'll see why that is true in a second. And because h small is exactly the sine of theta, we have proven that the sine of theta is less than theta. The height of the red triangle is less than the arc length, so sine theta is less than theta. And this approximation gets very, very close the smaller the angle is. So for big triangles like this, there's a big difference. The sine of theta here is, let's make this a bit bigger. The sine of theta is 0.589, whereas theta is 0.630, so a bigger difference. But as you shrink theta down, the difference between the height of the triangle and the arc length gets very, very small. So here it's 0.183 and 0.184. They're extremely close together. So the smaller you make it, the more accurate this approximation is. So let's see this first part. Let's explain why is it true. Why is h small, the height of the red triangle, equal to the sine of theta? And this is actually just simple SOHCAHTOA. So the sine of theta is the opposite over the hypotenuse. And if we look at this red triangle, let's take a look at this red triangle. What can we say about this red triangle? So I'm looking at the right triangle living inside the red triangle where h small lives. So this triangle from here to here to here. This triangle, its height is h small. That's the opposite side of the angle theta. So the opposite side is exactly h small. And what is the hypotenuse of this triangle? Well, the hypotenuse is exactly a radius of the circle. The hypotenuse is always on the unit circle, and therefore, because the radius is 1, we know that this is 1. So the sine of theta is h small divided by 1. That's the same as h small. Okay, so h small is sine theta. The other fact is that the arc length, let's call this the circular arc length, that is equal to theta, and this is because theta is in radians. So now we've shown that h small is sine theta and the arc length is theta. Okay, but why is it true? Why is h small less than the circular arc length. And again, you can see visually why it's true over here, right? It looks like that line segment is a little bit shorter than this curved line segment. And you can make some kind of argument about, imagine you started at this point and you had to get down to this line. Which would be longer, going straight down or going along a curve? Well, going straight down is shorter, always. So the curve has to be a bit longer. That's one way you could argue it. But an even more straightforward way to argue it is going to be looking at areas. So looking at the areas, I'm going to say that the area of the red triangle is less than the area of the pi. I'm going to call it the pi piece. The pi piece. So the pi piece carved out by theta, that is bigger than the triangle. And that is true. That one is plainly true by definition. The triangle lives inside the pi piece, so of course it has a smaller area. On the other hand, we know a formula for both of these. So the area of the triangle is a 1/2 base times height. The height is h small. And the area of a circular pi piece, we know a circular pi piece, the area is 1/2 times the radius squared times theta. And again, this is only true if theta is in radians. So that's, again, important here for this formula to work. In our case, though, what is the base of the triangle? What is the radius? We know both of these things. The base of the triangle is the radius of the circle. It's 1. And the radius of the circle is 1. So this thing is actually 1. The base here is 1. The radius is 1. And so what is it saying? Well, canceling out the half, h small is less than theta. Okay. And so if you combine these two facts, that h small is sine theta, the circular arc length is theta, with this other fact, that h small is less than the circular arc length, you combine them together, therefore, the sine of theta is less than theta. So very good. We've shown that the sine of theta is less than theta, and you could try to say, oh, well, this means that the sine of theta is approximately theta. But there's a problem, which is that what if the sine of theta is a lot less than theta? So this just shows that the sine of theta is less than theta. We want to actually show that they're approximately the same. So, this isn't good enough. This is sort of like one side of it. What we would really want to have, is something on the other side that the sine of theta is bigger than theta minus a bit, or theta, let's say theta minus a bit. And if we could do that, if we could get this other side going, then we could sort of squeeze the value of sine. It would be squeezed in between theta and on the other side, theta minus a little bit. And as long as this minus a little bit is really, really tiny and getting smaller and smaller, then we'll know the value of sine of theta. So far we have 1/2 of the thing. To do the other half, we need another triangle. So far everything here is just half the battle. To see the other half, we are going to add a new triangle. So here you go. Here's the new triangle. Maybe you can already see where it is. It's a big blue triangle. So we had a small red triangle, and now we have a big blue triangle. And this big blue triangle looks like this. It's a right triangle with a base of 1, and it has some height. That's the height of the big triangle. And just like before, we said the height of the small triangle is less than theta. It's going to also be true that theta is less than the height of the big triangle. And it turns out that the height of the big triangle is the tangent of theta. So let's see why that's true. And again, you can see it visually here, but why is it true? Let's demonstrate it mathematically. And we'll get a new page here. So we're going to say y is the height of the big triangle, h big, equal to tan theta. That's one question. And the next question is going to be y is theta less than h big. Those are the two questions we want to answer, or explain why they're true. The fact that h big is tan theta is, again, SOHCAHTOA. So the tangent of theta is the opposite divided by the adjacent. Let's take a look at our triangle. The opposite side is exactly h big, so theta is over here in this corner. The opposite side is h big in the blue triangle, and the adjacent side is this length over here, which is exactly 1 because we're in the unit circle. So this is the tangent, this is h big divided by 1, which is exactly just h big. So that is explaining why it is true that h big is tan theta. On the other hand, theta is going to be less than h big. This is going to be by the same argument as before. We're going to start with the area of the pie piece, and we're going to say that that is less than the area of the big triangle. And on the other hand, we have formulas for these things. So the area of the big triangle is 1/2 base times height. The base, as we saw, is very easy in this case. The base is just 1. The height of the triangle, that's exactly h big. That's what we want to know about. And the area of the circular pie piece we did already. It is 1/2 times the radius squared. The radius was 1 times theta itself. And so if you combine these two facts together, cancel out the halves, you end up with that theta is less than h big. Just like we wanted. Okay, so we have another half of the sandwich now. Theta is less than h big, which is the tangent of theta. You might think, oh, I did it the wrong way, right? I wanted the sine of theta to be bigger than something. So before, with our red triangle, we had finally, we did all this work, and we got to the fact that the sine of theta is less than theta, and we wanted something on this side, right? We wanted to say that the sine of theta is bigger than something. Did I do something like that? Well, I have that the tangent of theta is bigger than theta, and so I can just rearrange this a little bit. If the tangent of theta is bigger than theta, well, tangent is sine over cosine. So let's write it like this: sine theta over cosine of theta. And if I multiply both sides by cosine, that's okay because cosine is positive here. Theta times the cosine of theta is less than the sine of theta. Okay, so this is the other half of our sandwich. We made 1/2 over here, sine theta less than theta. Here's the other half. Theta times the cosine of theta is less than sine theta. So if we combine both halves, we get that the sine of theta is squeezed between two numbers, theta, and theta times the cosine of theta. And before I said we should try to get theta minus a little bit, this is actually theta times a little bit. The cosine of theta is always between 0 and 1. It's always a little bit less than 1, even for really tiny angles. And so this is theta times a number that is smaller than 1. That's a little bit less than theta. And so this squeezing is what is going to make the fact that sine of theta is approximately theta true. On one hand, sine of theta can't be more than theta. On the other hand, it can't be less than theta times cosine of theta. And because these two values are on the upper and lower bound are approximately the same, therefore sine theta has to be equal to or almost equal to both of them. And you can see this visually with a Desmos graph. So here I have, let me plot three things. Let's plot, okay, what do I have here? I want to have, let me move this over so you can see the equations. So what do I want to plot? I want to plot three things. I want to plot the sine of theta. In Desmos, you got to do sine x. I want to plot x, and I want to plot x times the cosine of x. And according to us, the black curve, sine of x, is going to be sandwiched between the orange and green curves. So let's see, what does this look like? And look at that. It works exactly like we said. So the curve sine of x is sandwiched between the orange, x times the cosine of x, and the green, x. So it has to live somewhere in between. And because these two things are getting very close together, that is why we can get the value of sine of x is approximately x. To really see it, to finally finish off like super mathematically, what you would do is you would divide both sides by theta. And if you do that, you get the sine of theta divided by theta. On this side, you have theta divided by theta. That's just 1. On the other side, you just have cosine of theta. So the sine of theta over theta is squeezed between cosine of theta and 1. So in Desmos, what would that look like? We would just divide all 3 of these equations by x. And you would see that the sine of theta over theta, or sine of x over x here, is getting squeezed right towards 1. So because cos theta gets close to 1, so cos theta on this side is getting close to 1, and the other side is always 1. Therefore, sine theta over theta must get close to 1 too. And if sine theta over theta is close to 1, that's saying that sine theta over theta is approximately 1. If sine theta over theta is approximately 1, then sine theta has to be approximately theta. That's what we wanted to show. We're going to see later in the course that this is actually some kind of version of a limit. You can make this more precise by saying the limit as theta gets very small of sine theta over theta is 1. That would be a perfectly precise thing to say, and that would capture the fact that this black curve, even though it's not defined at x equals 0, is getting very, very close to the value 1 there. Okay, so hopefully that convinces you. Hopefully you enjoyed the pictures. If you want to play around with the triangles, there's a link in the description where you can do that.